This video corresponds to Chapter 8 in your textbook and introduces confidence intervals and effect size. The separate video will address power. So this is where we're going to start with an example. Hyde, Fenema, and Lamont found that mean gender differences in mathematical reasoning were very small. And you've probably heard that men and women differ on mathematical ability. However, they were looking at some different things, and what they specifically found is if you got rid of the extreme tails of distributions, the differences were smaller. So you got rid of the really, really smart kids who are boys, specifically. Then what you see is that the differences favored girls. So, and also those differences depended upon the kind of tasks. So girls were better with computation and boys were better with problem solving. But if you want to look at how those two distributions overlapped, you'll be kind of surprised to see that we can't necessarily draw good conclusions from a study just because it's statistically significant. We know that each distribution, we've got some women who are really awesome at math and some women who are not so awesome at math. And we've got some men who are really awesome at math and some who are not so awesome at math. So each of these distributions has a lot of variability, and there's overlap of these two distributions, even though there's a significant effect. If we look at the distributions of scores, this is what we find, that if you look at how much overlap we have, you see the dashed line here and then the solid line, basically, they're pretty much on top of each other. So what does this tell us? If we're finding something that's statistically significant, it doesn't necessarily mean that it's practically significant. So that brings us to talking about some different ways that we can think about what we're doing with hypothesis tests. Now, I'm going to address confidence intervals because I want you to know what they are, but we're not really going to spend a lot of time on computing them, essentially because of the condensed nature of this class. So let's talk a little bit about confidence intervals for a minute. Confidence intervals are an interval estimate. When we have what's called a point estimate, we're looking at a summary statistic. It's a single number that's an estimate of the population, something like the mean or the standard deviation. Those are both point estimates. An interval estimate is based on a sample statistic, and it gives us the range of sample statistics we would expect if we repeatedly sampled from the same population. So we're talking about this as being a confidence interval. That does sound kind of familiar, or at least it should. Isn't this what we did with the central limit theorem form, where you had the penny ages and you repeatedly sampled and you got mean scores for different sample sizes? So if we continue to do that, we could say if we repeatedly sampled from this population over and over again, what range of means would we expect to get 95% of the time? So that's really what a confidence interval is getting at. So a confidence interval is an interval estimate that includes the mean we would expect for the sample statistic a certain percentage of the time if we were to sample from the same population repeatedly. Now, the standard is typically to say 95%, and this is kind of the complement to our p-value being 5%. So if you look at alpha, which is our type 1 error rate, we're okay with making a mistake 5% of the time, as long as 95% of the time we're making the right decision. So that's what's coming back with this confidence interval. What would we expect our mean in the sample to be if we repeatedly drew samples from the population and calculated all of those sample means? And we want to be right 95% of the time. So what a confidence interval gives us is the range around the sample mean when we add and subtract a particular margin of error. And it gives us the same results as hypothesis testing, where we're looking to see, is our score more extreme than a particular critical value. But it does add some more detail because it gives us the range of values that we could expect to get. So let's say that we have a mean of 232 and we want to set alpha to being 0.05 with a two-tailed test. So that means we split that alpha, that 5%, into 2.5% and put it in each tail. So that's the first thing that we need to do, is figure out, okay, what would these cutoffs then be if our confidence interval is 95%? So the first thing we need to do is to find out what these z-scores are for the cutoffs. Now you're going to notice after a while that with the z-distribution, it's one distribution, so you may eventually become very familiar with plus or minus 1.96 as being the cutoffs when alpha is 0.05 or when we're looking at a 95% confidence interval. So right now we know that the mean of the z-distribution is 0, and we need to figure out what these raw scores are. So if we were to do the math, and you do know how to compute raw scores from z-scores now, given what we've talked about in the last chapter, but instead of going ahead and doing all that math for you, I'm just going to show you that we know it's plus or minus this particular amount, and so our lower limit of the confidence interval is 219.54, and our upper limit is 244.46. And this is, again, our sample mean. So we would say if our population mean is outside of this range, then it's unlikely that our sample was drawn from that particular population. Okay, so which do you think is more accurately representing the data, a point estimate or an interval estimate, and why? And what are the advantages and disadvantages of each of these two methods? Just some things to think about before we go on to talk about effect size. And effect size, remember back to our example, that difference, the overlap that we saw was really big between the genders for math ability, but it was statistically significant. So effect sizes really get at just how big is the difference between our two groups. Does significant mean it's a big difference? Or does significant just simply mean that it's different enough that we're pretty confident they're from different populations? Generally speaking, it's that second one. And sometimes it's also the first one, but not always. So you could have a big difference, and you could be pretty confident that they're from different populations, or you could have a really tiny difference, and, well, that means that maybe that confidence is not as great. So there's a number of different things that will allow us to be more likely to find a statistically significant effect. And you'll see this again when we look at power. But if you have more people in your population, or I'm sorry, in your sample, then what happens is that standard error gets smaller and smaller. And so then it's more likely that there's going to be less overlap and we'll find a statistically significant effect. That's also why when you look at things like epidemiological studies, gosh, they have these giant sample sizes. And part of that is just because, you know, they're looking at low frequency occurrences anyway, like say they're looking at vaccine injury or something. Those things don't happen very frequently in terms of, would we even expect if we sampled 100 people to see any vaccine injury at all? Well, probably not. And so we'd probably need a sample size of 10,000 or 50,000 people. But that means we can detect really small differences. So it doesn't mean that that difference is a very large difference in terms of magnitude. So this brings us to what is an effect size. And it's basically a way for us to figure out what is the size of a difference that we have, and we can compare across studies. It's not affected by sample size, so we're really removing that part of sample size out of the equation, and it can give us a standardized way of looking at how big of a difference we're finding. So here's some different ways that we can look at this. Imagine that both of these two sets of distributions represent significant effects. Which effect is? So if we look at these two, you can see the sample means are these vertical bars. So which of these two effects is bigger? If you said the bottom one here, this is a bigger effect. And you can see that too because there's less overlap between these two different distributions. And here, that different effect is the variability of the different distributions is the same, but the means are further apart. So that gives us a bigger effect that we can detect. Here's another example. Look at the spread. This is what we varied here. The mean difference is the same, but the variability is different. So which of these do you believe would have a bigger effect size? If you said the bottom one, then you're correct. Because again, there's less overlap between these two distributions of scores. So here we see that we can detect this effect better. Okay. So essentially what we want to do in order to increase our effect size is to decrease the amount of overlap between the two distributions. So if we make the means farther apart, that will give us a bigger effect size. And if we make the variation within a population smaller, that would also affect the magnitude of the effect size. So in order for us to calculate an effect size, and you'll see that this comes up for basically every test that we have that involves two different means, whether it's two sample means or a sample mean and a population mean. And it's called Cohen's d. And it looks at the difference between means using the standard deviation instead of the standard error. So it does look like your z-score formula, okay? But now this is not sigma sub m. It is just plain sigma. And that allows us to remove the mean from the equation because remember, this is sum of all the scores divided by n. This is also the sum of all the scores divided by n. And this is sum of the squared deviations divided by n. So we're getting rid of that n because they all have that as a common factor here. So it's the difference between these two divided by the variability. So that's how we get effect size. Now, there's several different ways that we can interpret effect sizes. And again, Jacob Cohen, he's the guy who developed all of this stuff. And he came up with conventions for interpretation. He said a small effect is an effect that is 0.2. A medium effect is somewhere around 0.5. And a large effect is somewhere around 0.8. Now, you can actually, this is not like a correlation where you can't go above 1. You can actually get effect sizes that are like 1.3 or 2 or something like that. And those are very large effects. So this is just to kind of give you a sense of how big of an effect, what's the magnitude of this effect that I found. So these are kind of rough guidelines to help you interpret what your effect size means. Okay, so in the next video I will be talking about statistical power, and I've also posted links to an online stats resource for the Power Forum where you can go and watch some other point of view, I suppose, on doing power analysis and why it's important. So that's introduction to confidence intervals and effect size. And if you have other questions, please let me know in the homework forum.